Hello, my name is Jeffrey McKelvey, and this is Lab 5, the Choose Your Own lab, and I chose to do a transfer of momentum lab. So the purpose of this experiment was to observe and analyze the collision of two billiard balls to attempt the creation of a perfectly elastic collision while comparing it to an elastic model and finding the original force exerted on the first ball. My result was that an elastic collision was not possible in this situation, as it is realistically an extremely difficult situation to create. However, something similar was produced, and the original force on the ball was found to be 72.084 newtons. So the setup of my lab was I had two billiard balls on a pool table, and while one was at rest, I rolled one into the other and observed the transfer of momentum. Both of the balls have a mass of 0.16 kilograms and a radius of 0.0285 meters. This information was taken from the internet because billiard balls have a standard size and mass. The initial velocity of the first billiard ball, the lower yellow one, was 0.0873 meters per second, and the initial positions, the origin was placed at the center of the first ball, with the second ball being 0.89 meters above. And due to the fact that the ball rolled straight upward, only the y coordinate is taken into account here. So, in order to understand this lab, one must have a background in the physics. So, the law of conservation of momentum states that the initial momentum must be equal to the final momentum within the system, and the law of conservation of energy states that the initial energy within the system must be equal to the final energy of the system. And the energy in this case is composed of the gravitational potential energy plus the kinetic energy. And for the purposes of this lab, the gravitational potential energy does not truly play a large role. Yes, it is still present. However, because it is on the z-axis in this case, and the z-axis never comes into a role as the ball is rolling along the xy plane, kinetic energy is all we are really going to look at for this lab. So our total kinetic energy is composed of the rotational plus the translational kinetic energies. And K rotational can be found by multiplying 1/2 by the inertia by the angular momentum squared. So our inertia is that of a rotating sphere, which can be found with the formula 2/5 times the mass times the radius squared. And our angular momentum can be found by dividing the velocity by the radius. And then K translational can be found by multiplying 1/2 by the mass by the linear velocity squared. And so that all takes place and is being calculated once the ball is in motion. However, in order to find our original force, one must simply look at the change in energy, which is the change in kinetic energy from before the ball started rolling, which was 0, to the kinetic energy that was calculated once the ball was in motion. And so because work is equal to force times distance, one can also know that force is equal to work divided by distance, and in doing so we obtained our final answer of the force being 72.084 newtons. Here we can see a graph comparing the movements of the perfect ball, so the perfect virtual model compared to the observations that I gained from tracker I had to do this in Google Spreadsheets because due to an incompatibility problem with my computer's operating system and hard drive with the Python program, I was not able to upload my CSV file after tracking the the ball's movements in Tracker. So here we have the energies involved in this lab. We have the translational, rotational, and total kinetic energies of both of the balls. And as you can see, there is a beautiful transfer of energy from one ball to the other, and it is a seamless um, collision. This is sadly only from the perfect virtual model because I was unable to upload again the CSV file to Python. However, I was able to put the collision as being the point at where the distance between the two balls or the two centers of mass was equal to the sum of their two radii, which means that so when they were that close, then their edges must have touched and the collision would have occurred. And so the outcome was an elastic system was not able to be created. However, something similar was, and both the law of conservation of energy and the law of conservation of momentum were proved to be true. And again, the initial force of the throw was found to be 72.084 newtons. Um, my possible reasons for error included the angle of the force originally being applied to the billiard ball. If the force was applied downward or at an angle as opposed to straight forward, that could have caused an issue that I did not originally consider. The other is that it is a felt table, and while on a flatter surface such as linoleum, the static friction would not ultimately have detracted from the rolling. The felt and the texture did, and there is, of course, always the possibility for tracker error, which is an inevitability with any lab. Thank you for listening, and happy final season.